We can start again. So we saw the piezoelectric case. Now let's see the electromagnetic one. So you will therefore have a law of induction, Laplace force, and so on. And when you make kind of macroscopic analysis, you have something very similar. Okay. Not a current but a voltage source, still controlled by the velocity, and you will have a force depending not on the voltage but on the current source. Because between electromagnetic and electrostatic particular relationship. What is this relationship? When I go from magnetic to electric system, what kind of transformation there is? Yeah, but more in the physical explanation. Kind of between mathematical and physical, conceptual link between them. You see that here I'm moving from a current in the piezo case to a voltage, and I'm moving from a voltage to a current. Yeah, but more in terms of conceptual explanation. Physical explanation. No, very conceptual one. You know the game? Okay, start.
We have vowels or not?
Let's start without any. Otherwise, it's too simple. Say a letter, not vowel. Say a letter, not vowel. A letter.
F.
Whose turn? No, that's only one. So I want another letter. No vowel. We will take the vowel if it's very close to death. No. So letter, not vowel. O, not vowel. L. Only one. Is Y a vowel? T? D? Only vowel, no. Duality, exactly. It's the dual transform when I go to the magnetic to the electrical system. So that means everything, conceptually everything we saw for a piezoelectric generator apply to a magnetic one, but you have to change the current to voltage, the voltage to current, capacitance to inductance, okay, resistance to conductance or resistance, but basically it's the same, except that because of this dual transformation, if I work in low frequency with capacitive system, I should work in high frequency with electromagnetic system, which is not the case. That means that here we have the inductive behavior usually negligible with respect to the losses. If we are in true duality, that would mean we have also a transform of the frequency. And with the frequency, we will have the inductive behavior that would be preponderant over the resistive one, which is not the case because we stay in the low frequency region. Okay, but otherwise we can see that's very similar. Okay, between the piezoelectric effect and the electromagnetic one. It's just a matter of transform. Okay, and we will also for the optimal impedance and so on. Actually, it was written. If you look at the slides, it was all. And for the simulation, it's also the same things, except that also instead of using using the control voltage and current source, you invert them in terms of control, and it's you have exactly the same schematic. Thermoelectric system. So thermoelectric system, they are described by 3 different effects that actually are the same effects. Okay, it's the same physical explanation. It's just another way to describe it. There is the Seebeck effect, that is the temperature to electric conversion. Peltier effect, which is the contrary, and Thomson effect, which is actually a particular generalization of the Peltier effect to a thermal gradient inside a thermoelectric module. Okay, so I show you a true thermoelectric module. So you can see there is some p-n junction. Okay, that make the legs, the small legs we saw, and you've been able to see on the thermoelectric system. And what we have is that in a thermal configuration, all the legs see the same temperature difference, so they are thermally in parallel. But in order to increase the voltage in terms of electrical connections, you see they are in series. That made some things like this, some kernel like this. Okay. So how to model it for electrically speaking? So in terms of electrical model, it's very simple. It's just a voltage generator with a resistive internal impedance. So that's this, the model. And in terms of thermal model, on the temperature side, you will have classically the thermal conductivity of your module. You will have, because it's also a conductor, you will have some Joule heating due to the current, so that will produce some heat flux. So basically, with this representation, the current is the heat flux, and the voltage is the temperature difference. Okay, so that's why we can see here that the difference over this resistance is actually the voltage difference is actually the temperature difference. And here you have some heat flux due to Joule heating, because there is current that is going there. You can see that we separate Joule heating into 2 half Joule, so into 2 sources, with each one being half of the Joule heating. We have also here and here the Peltier effect. Be careful, here it's the H for hot side. Here it's C for cold side, so it's not the same heat flux on each part. And of course, you have the true thermal conductivity that can be modeled in the electrical domain by resistance. When we are doing energy harvesting, actually, we don't have hundreds of amps that are going through the system, so we can neglect the Joule heating as well as the Peltier effect. That leads us to an example from what I said. Sorry, actually, I just added recently, it's not on the handouts, which is some people get funded of several hundred thousand euros because they said we can harvest heat body. Okay, let's imagine what happened. Sorry, I just cut it because not to shock you, it was a photo of a naked body. So let's consider our system and trying to model it. So I will make it very, very simple. My body is a semi-infinite medium, okay, with as a first approximation, constant temperature. Then I have a potential air gap between the skin and my thermoelectric module. Then I have my thermoelectric module. And finally, I have the surrounding environment, so air, which is also a semi-infinite medium. I defined all my parameters. So the section, the thickness of the TEG, you saw on the TEG 5 millimeters, that's in the right order of magnitude. And finally, the thickness of the air gap, which is actually something that we can make varying. Okay, I define also all the temperatures, so the ambient temperature, the temperature on both sides of the TEG, and the temperature of the human body. And as I said, we'll consider that it's approximately constant with 30 degrees. Let's try to see what happens. Implement it with here the thermoelectric module. Okay, here I said that the temperature of the human body, we can consider it as constant, so it's a constant voltage here. The resistance, conduction resistance of the air gap, okay? And here we have also the resistance that represents the convection and superficial exchange of heat, okay? And finally, I have ambient temperature. We said, of course, that we can remove the sources because the current is very small and there is no significant impact in terms of Joule heating or Seebeck effect. So it leads us to 3 resistance. It's quite easy to compute, to derive analytically the expression of the temperature difference. It's just temperature difference on the TEG is just the TEG resistance over the sum of all the resistance times the total temperature difference. I take some typical values for example, for the heat exchange coefficient, for the thermal conductivity of air and the TEG, and so on. Okay, that gives me varying resistance for the air gap. Okay, so resistance in the temperature domain. For the TEG, it gives approximately 10 ohms, and you see here already that it's 20 times higher for the resistance that represent the superficial exchange. So that means if I have, for example, a 10-degree difference between my skin and the ambient temperature, because of the superficial exchange, I have less than 0.5 degree within my TEG. This is what I told you previously. We need to think about the system within its environment. That's not because I have 30 degrees here and 20 outside that I will put 10 degrees of gradient within my TEG, because it has a very high thermal conductivity. Okay, that doesn't work. It has a very high thermal conductivity, sorry, here, and so it's almost impossible to maintain the gradient inside. And from 10 degrees, we have 0.5 that it can be actually used. Okay, and then people get anyway from it for this. Well, that's okay, but actually needs to be very careful with this. Oh, sorry, there is a small typo here. So very small temperature gradient within the TEG. That means very small power, because the power depends on the squared temperature. So that means here we have 20 times less temperature than what is expected without a little bit thinking about it. That means you have a factor of 400 when consider the energy. Then you can go to forced convection. Okay, we'll do just after here, but you can see, for example, in terms of voltage, it's voltage in the range of microvolts or 0.1 millivolts, and in terms of power, it's 20 microwatts. We can use forced convection or heat sink. Okay, you can easily increase the coefficient of exchange by a factor of 10, but again, you have 3 degrees, 3 Kelvin instead of 10 within the TEG. And actually, when you are using this, the thickness goes from this to this, okay? Because the size I don't know if I have an example. The size of the exchanger is very big. Okay, you see the fans and so on. Fan, of course, we won't supply a fan, but just a kind of passive heat exchanger. It takes also a lot of space. So you are also decreasing a lot the power density. So that's why thermoelectric modules, they can be interesting for thermal gradient, but there is definitely there is a big open field for pyroelectric system and so on, and the challenge here is to convert spatial gradient into a time domain variation. There are some heat engines, for example, that use ferromagnetic materials that get that can be attracted by a magnet, and when they hit, they lose their magnetic properties, so they are released with a beam, and then they can convert spatial gradients, spatial temperature gradients into movement that can be also converted to temperature time domain variation. Okay, pyroelectric system. So you have something very similar to piezoelectric element in terms of constitutive electrical equation, except that instead of having the strain or the stress, you have the temperature. And the other constitutive equation is actually thermodynamic equation that gives the entropy. So usually, as I said, the coupling of such system is quite low. So we can neglect the thermal effect and forget about thermodynamics. Okay, especially I guess for the students it's still a nightmare. Actually for me it was, but now I'm more or less happy with it or using it. But anyway, so here I can just, by neglecting the backward coupling, I can just model it by a current source that is controlled by the temperature derivative with capacitive internal impedance. So very similar to the case of piezoelectric, when we also consider that there is no coupling and no mechanical effect of harvesting or doing anything on the electrical side. So let's go now finally into one electrical interface, that is load optimization, and more precisely load adaptation. Of course, if I consider a thermoelectric system, it's DC voltage. If I put a load, the power will depend on the load that put at the end, okay? And there is an optimal load, quite easy to compute, that allows maximizing the voltage, the power, sorry, typically half voltage. And you understand also that the problem is that when I will connect my sensor, whether my sensor is in sleeping mode, is in idle state, transmitting state, and so on, it won't consume the same energy. So that means it won't present in an equivalent way the same impedance to the system. So sometimes we will be here, sometimes it will be here, and so on. So it's quite difficult to ensure in such conditions with varying kind of operation that we have something that is operating at its optimal point. The same for pyro-piezoelectric system. So here we have AC source, so we can either consider AC energy harvesting with, for example, a load that mimic, for example, a converter. And with frequency analysis, we can see that we have also very similar expression. Okay, I used in the frequency domain that I get the power with the multiplication of the voltage by its conjugate divided by twice the resistance. I have my expression. So X is either mechanical parameter such as the displacement or a thermal parameter for pyroelectric system. So the maximum temperature, the temperature variation magnitude. Okay. And here we have also the optimal load, that is not surprising at all. Here we have exactly, in terms of magnitude, the load of the source itself. That depends on the frequency, actually. And again, we have something that depends on the value of this load. Okay, this is either, and instead of just harvesting on a simple resistance, we want, in order to supply microelectronic system, to rectify and to benefit from a DC voltage. Like, okay, so by using $100 circuit, by using rectifier that will actually ensure that whatever the current flow with the piezoelectric element, that the current is always flowing on the right direction here, with a smoothing capacitor that will allow that we have a constant voltage output at the end. Okay, so how it works? Here I have my beam that is vibrating until the voltage reach either the absolute, the rectified voltage, either plus the rectified voltage or minus the rectified voltage. At this time, there will be charge transfer. The voltage will be clamped, and there will be charge transfer from the piezo to the load or to the intermediate storage capacitance. Okay, until we reach a maximum value, because in this case we have, in this case, when the voltage is clamped, we just have the current that it depends on the velocity, because the term here, this term is 0, because the voltage is equal to VDC, so its derivative is 0. So we have only this term, and when the displacement is maximum, so there will be an inversion of the velocity that will go, for example, from positive to negative. And so therefore, the current will tend to inverse. That will actually block the rectifier bridge. So that's why we have here this decrease. Okay? And in between the two conduction states, actually we are in open circuit. So the current is 0. So that means that the voltage varies with the displacement, and we don't have to forget about integrating constant k, for example, here, to get the right expression. This is actually what I said exactly here. From previous conduction, for example, from here. So here the displacement was minimum, okay? And because the velocity change signs, that will make the current changing the sign, and the rectifier bridge will be blocked. So that means that here we will be in open circuit condition with initial conditions that consist in the voltage here. So we consider that the rectifier bridge is perfect. Okay, so no voltage gap on the diode. So here we have minus VDC, with VDC that is the rectified voltage. That is equals to minus alpha over C0 UM, and therefore, if we put it in this equation, we have the voltage equation that will depend, of course, on the displacement, but also with this term that corresponds actually at the end of the conduction, and that corresponds to the integration constant I was speaking about. Okay. Then we'll look at when there is the next conduction. So I'm here. Open, 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 until I reach the rectified voltage. In this case, there will be some conduction, and there will be a current flowing from the piezoelectric element to the load and the capacitance here. So it happens for displacement that have been noted U1. This value of U1 will be very important after to compute the harvested energy. So I can get U1 directly as a function of VDC and UM, because here U1 corresponds to VDC, and we have already a relationship between VU as a function of the displacement magnitude and the rectified voltage. So I can get this expression, and then I'm actually harvesting when I'm on this plateau here, okay? And the harvested energy is nothing else than the integral of the voltage by the current. Here the voltage is clamped; it's just VDC. Because the voltage is clamped, the current is just alpha U dot. So I'm integrating U dot dt, which corresponds to integrating du over U1 and UM. Because I start harvesting at U1 and I finish harvesting at UM. Okay? So it gives me an expression of the power harvesting happens twice a period. So to go from the energy to the power, I multiply by twice the frequency. Okay, and then I get the expression, a function of the frequency, the rectified voltage displacement magnitude. However, this power is also the squared voltage over the resistance. And so it allows me to get the power actually as a function of the resistance. Okay? And again, I can say that there is an optimal resistance that exists for maximizing the power. So again, we have an issue in terms of load adaptation. This is not finished, because here I consider that I have fixed displacement magnitude. But actually, in most of the case, this is not the displacement that is imposed. That is the excitation, either the force or equivalently the acceleration, because I can also represent there's something also interesting in terms of that's also something interesting in terms of modeling is we can see that actually this equation we can also show that so this equation is when I apply a force. However, I can also have what is called seismic or kinetic energy harvesting. It's not applying a force, it's applying an acceleration. And in this case, we can show quite easily that the expression is very similar, but except that it's not the absolute displacement, it's a relative displacement of the mass with respect to the base. Okay, so it's the elongation, and that the force becomes just m times the acceleration of the base. Okay, so it's exactly the same. Just have to replace f by m times the acceleration. You have the same equation. Okay. And when I consider that actually the excitation is the actual input, I may have some mechanical effect of harvesting. Okay. And when I take this equivalent mechanical damping, you can say that the value either in AC or in DC. For DC, I do the energy balance considering monochromatic excitation and response at the resonance. So we can see that the displacement magnitude will depend, of course, on the excitation magnitude and the mechanical damping, okay, but also on the electrical aspects and electromechanical aspects. Of one frequency. And in this case, what happened is that you have a damping effect, and you have also to consider it in there. You have to replace U here. You have to replace U by its expression as a function of R, because here the input is actually the force or the acceleration. Okay, and what happened when we compute this is that you can see that we can use what the k squared qm that was already more or less discussed previously. So k squared qm is something very important in linear harvesters. In nonlinear harvesters, mechanical nonlinear harvesters, it's a little bit more difficult. You can ask Thomas about it. But for linear harvester, it's it's a very important parameters. Why? Because physically speaking, QM gives you the amount of energy that is entering within the structure. If QM is high, that means you can have, for a given force, high velocity, and thus incoming energy is the force times U dot times U dot. If you have big velocity, you can have a lot of energy entering. So this is the first part. The second part is QM, is K. So the electroactive electromechanical coupling coefficient that has been discussed a lot by Professor Mickael, that give the amount of energy that is converted with respect to the input energy. Okay. So that means how much of this energy that enters into my structure I can convert into electricity. So you see there is these two aspects: input energy and how much I can have in terms of conversion. So that's why it's an important parameter. And actually we can also express it here, because with this modeling, you have the value of k squared that is equal to alpha squared over C0 k e plus alpha squared, or in other words, alpha squared over C0 kd, with kd that is the open circuit stiffness that is given by ke, the short circuit stiffness. Okay, and here the stiffness is corresponding to the mechanical stiffness when I don't have any voltage, so 0 voltage, so constant electric field. That's why we put this E as a superscript. And Kd is the open circuit stiffness with 0 current. So 0 current, in 0 initial condition, we have V equals to alpha over C0U. If I put it here, I can write only the mechanical equation, but instead of having Ke, I have Ke plus alpha squared over C0, and I can replace it by Kd. Okay. So this parameter K squared is very important, but again here be careful. The K squared is the structural one, not the material one. Okay. And you see, as long if I increase k squared qms, that means I increase the effect of harvesting on the mechanical side. There is a change in the optimal resistance, and actually at one point there is a split. Okay, so that means here the optimal resistance not only depends on the parameters like the capacitance and the frequency, but also on the electromechanical conversion effect. Okay, and the second thing is that if I'm looking at the maximum power as a function of k squared qm, so I imagine that at any point I can have the maximum resistance. If I'm looking at this, there are two things. The first one is that in AC energy harvesting, I can slightly improve my harvesting system. Be careful, usually in terms of efficiency of energy converter, of electrical converter, efficiency is much lower in AC, so we lose what we gain here. Okay, but the most important one is that here I have a plateau. Okay, there is a power limit. Actually, the power limit depends also on the losses, but there is a power limit. That means if I increase, not the QM, because the power limit depends on QM, but if I increase the performance of my material, for example, so I increase the value of the electromechanical coupling coefficient, I won't harvest more energy. All the effect will be in terms of damping. Okay. So it's not necessary here to buy a material or a material that costs 1,000 and 1,000 euros for just a very short, very small sample, while you can be here without any significant loss in terms of power, but with a much cheaper material. So in electromagnetic systems, it's very similar in its AC operation. We neglect the inductive behavior. We have something very similar than thermoelectric, but in AC operation, but the principles are the same. Again, we have an optimal resistance. In DC operation, we can also do something very similar to what we did in the case of piezoelectric systems. It's a little bit more difficult here because there is not the current continuity, because we are neglecting the inductive effect compared to the resistive one. So there is a little bit more subtleties in terms of what happens when I'm going from the end of a conduction to the next one. Okay, but otherwise the concept, the steps, they are very similar. Okay, and again, also like in the piezoelectric case, when you have high coupling close to the resonance, you have a damping effect that also modify your optimal load. Okay, so you see that we cannot design a system just considering the electrical aspect. We have also to consider the mechanical aspect to have a global optimized system. Okay. So we saw here that we need something to, we have some load that optimize the power. So how to ensure that we are always optimized, whether our system is operating in transmit mode, in sleep mode, in any kind of mode, is just to put something in between our input electrical energy and load that will first make the piezoelectric element seeing the same the same input impedance, whatever the load. And how to do this is just to ensure that the energy never goes directly from the piezo element to the load. So we use an intermediate energy tank for this. There is also automatic approach with MPPT. I think MPPT, where we are dealing with 100 of microwatts, it's too challenging to implement. We can make some kind of hybrid approach, but through MPPT, usually it's for kilowatts, the true MPPT itself. There can be some variants we can more or less adapt. We'll see some of them. But here, the most interesting approach, to my opinion, is to use DC-DC converter, DC-DC switch converters that operates in discontinuous mode. Okay? So there are typically 4 architectures for this. Step down, boost, buck boost, flyback. Here, the principle is to close a switch very quickly. So here, for example, we close the switch so that the voltage source, which is actually our transducer, charge the inductance. Then we open and the inductance discharge in the capacitance. Here, it's actually the contrary. There is just a flywheel diode here. One very interesting, and I will explain why, is the buck boost. Because in the buck boost operation, this is exactly what I explained, we will never have the piezoelectric element connected to the load. And this is why, actually, there was some research on the step down. It was, to the best of my knowledge, the first paper published on this principle is on a step down. Maybe it's from Imperial, actually, I don't know. No, it's from US. But what is interesting with the buck boost is that the energy flow is from the source, so the piezo, to the inductance. Then we disconnect them, and the energy stored in the inductance is then transferred to the load, to the storage stage and the load. So there is never direct connection between the piezoelectric element and the load. And like this, we can have kind of load adaptation by playing with the parameters of our buck boost system. Okay, so I will give you the example here. We can have this kind of load adaptation. But one very important thing is that we need to be in discontinuous mode. Okay, so how it works? First, I close my switch. So here it's a transistor, but it's like a switch. Okay, I close my switch. The piezoelectric element discharge through the diode. We'll assume that the time constant are high enough so that we can consider that the current increase linearly. Okay, so the current from the piezoelectric element or an intermediate storage element increase linearly. That means we are transferring energy to the inductance. Then, and here the diode is blocked, so that means we are not connected here to the battery here. Then I open my switch, okay? So that means I disconnect my capacitance, my rectifying capacitance from the inductance, okay? The problem here is that with the inductance, what happens if I have a current flowing through an inductance and I open the switch? Inductance don't like seeing sudden change in terms of current. Okay, you agree that the voltage of an inductance is related to the derivative of the current. So if I open suddenly, I have this that goes to infinity, and you will have this strong electric discharge and so on. It's not that nice. Okay. Sometimes you can even burn the inductance if it's very, very high power. So the inductance will try to find a path to get rid of the energy it has stored. But actually, the current flowing like this, there is this path that is possible. So actually, when I open the switch, the diode starts conducting because the inductance can discharge and transfer its energy to the battery. This is what we see here. Okay, and this is how we can transfer. We're in 2 steps, so without connecting the piezoelectric part to the battery directly. This is how we can do this 2-step transfer that allows to have something that permits having load adaptation. Because if I'm looking at here, the switching frequency is very high. Okay, the frequency is very high compared to the vibrational frequency. So if I compare, if I try to have the equivalent impedance, because the switching being high, as I'm in low frequency, I can consider that I can do the equivalent impedance. You can see that the equivalent impedance seen like this is fixed by the inductance, the duty ratio, and the switching frequency. You see, there is nothing about the VBAT or any connected resistance here. So totally independent from what is connected after. And I can tune this value to be actually on this point here on the maximum values. Okay, I can tune the value to be, for example, here in order to maximize the harvested power. Okay, so this is an example with the buck boost. Buck boost is very nice because it's theoretically totally independent from the load. However, we need to be in a discontinuous mode, and for this there are some conditions on the rectified voltage with respect to the load voltage itself. D'accord? We can use it either in DC operation, so you see here that I'm after a rectifying diode, so that means that my system is actually here. It's playing the role of RL, okay, with a constant one, whatever is after. Or I can also consider, from what we said, that in AC we can harvest maybe a little bit more. We can here not using any rectifying capacitance, and in this case we have this kind of voltage, so still kind of more or less sinusoidal, so more or less AC harvesting operations. However, as I previously mentioned, in this case, it's more difficult to have an efficiency as high as the other one, okay, but it's still working. By the way, here in this one, if you read this paper here, you can see that there is also, it's combining the principle of the buck boost converter in DCM mode with kind of sensing to play, if I remember well, with the duty cycle, in order, so kind of simple MPPT. So that's why here I said there is also a kind of MPPT, which is possible to implement here as long as there is several milliwatts that can be harvested. I have my piezoelectric element. To make it simple, we'll consider just the electrical aspect. We'll say that there is almost no coupling, so that the displacement is fixed, the displacement magnitude is fixed, and we can just consider only a current source, okay, for this. So basically, first we'll make we'll do it like this, that will be easier. Hop. Start back to the same thing I used previously, except that here we said that we're no longer considering that there is a mechanical effect, that the coupling is quite small, so I can just use a simple current source. Okay, so I can take a simple current source. So I go to the components and then just select current, which is a simple current source. So I select it, rotate it, for example. Okay. I don't need the load. I still have my my capacitance, so I will keep it. Then I will define the parameters of my source. It's not a DC source, okay? It's an electrical harvester. They are meant to be used in dynamic operation. So I go to advanced, and here I have much more choice. And in our case, we'll consider the sine exciting source with no offset, amplitude, I said 1 milliamperes with a frequency of 100 hertz. Also, to ensure that I will have a sine with 0 offset, because here I have 0 current offset, but I also want 0 voltage offset by charging a capacitance. I put also 90 degrees here. It's to be sure that in terms of voltage across the capacitance, I'm between 0 and 10 volts, for example, but between -5 and 5, so centroid as well. By the way, previously I didn't show you, but you can also use the software to make some small signal analysis, some frequency analysis as well, and you can define it in the source here. And then you can also define it in the simulation parameters. So here I define my current source, okay, with its given amplitude, frequency, and I added a kind of phase lag in order to be sure that if I run it, so for example, stop time, let's say 100 milliseconds. Usually the first and the last box is to tick in order to make it more stable. Okay, and here you can see, I will call it PZT, for example, instead of out. And here I have effectively a voltage that is varying with 0 mean value. Yeah. Then after I will add the diodes. So the diodes, it's here. Okay, you can have them directly. I would advise you not to use the general diodes or to use the general components. And here, if we right click, we can pick a diode. And here you have all the reference of the diode that are included within the library. Okay. And so this is a diode you can buy, and here this one is one of the most classical diodes you can find. 1A 4148, and there are the different electrical characteristics that we don't care about right now. We don't need to consider about them. It's a typical diode, quite frequent, very cheap. So no problem about this. So we'll use this diode. It's always better to use a real component rather than using a generic model. Okay. So I have the diode. I will copy it in order to make my rectifier bridge. Okay, so I just copy. To copy, it's as usual. It's Control C. Okay, so I have my rectifier bridge like this.
is exactly?
It's NMOS. It's transistor. No problem. And here it's not B1 anymore. It's just a simple current source now. Because it's not controlled anymore. We consider that there is that the mechanical aspect is not modified, so that we can just consider the electrical one. Okay? Yeah. So for the current source, this time it's not a controlled current source because we get rid of the mechanical aspect. We said that the coupling is quite low, or that we have actually the displacement that is imposed. So it's no longer a controlled current source, so you have to remove it and to place what the current source itself, so that is called current. Yeah. NMOS, but I will discuss about it later. What about the netlist? With wine. Okay, perfect. Okay, now I can add also capacitance.
Il se connecte en fait. Il faut soulever un peu
Oui,
plus.
faut pas que ça soit sur le nœud. Ouais.
C'est ça.
Ouais, parce que si on fait passer un fil à travers la
truc,
connectite, ça se connecte automatiquement. So now I can add a capacitance and can put, for example, 4.7 microfarad. Why 4.7, not 5? Why here, when I take more or less randomly the value, why did I put 4.7 and 5? It's normalized value. Okay? You write U and it will automatically recognize micro. Then I will label the nets as previously. Okay, for example, rect P to say rectified positive, and here rectified negative, rect M. Okay, I'll launch it again. So, compared to previously, you see first that here there is a transient for charging the capacitance. And you can see here we have the plateau that we previously saw. Okay? Because if I'm looking at the rectified positive and the rectified negative voltage, so I will look at the rectified voltage itself, so it's no longer the same reference, so it's not referenced to the ground. I have something like this. Okay, so now we have our standard harvesting stage. If we put a resistance here, we can show that if we change the resistance, we'll have a change in the power, in the harvested power. So what we will do here is to actually implement our converter. So first, we put our inductance. So with 200 millihenries. Then we can put our switch. So in our case, our switch will be a MOS transistor, N-channel MOS transistor. So it's NMOS in the component library called NMOS. So I will place the NMOS. Be careful. Actually, you don't have to rotate it or anything like this, because you have the drain, the gate, and the source, and you have to leave it like this. Okay. However, as for the diodes, we won't use the generic model, especially for the MOS. It's not that nice in our case. And we will sort with the part number, and we'll take this one, 2N 7002. Okay, so I will use my voltage source to control my transistor. Okay, so I connect the voltage source between the source of the transistor and the gate. And then I will define the waveforms that are applied. So here we want on-off. So we'll use pulse control. So in terms of voltage, it will vary between 0 and 10 volts. Okay. The frequency will be approximately, let's say, 3 kilohertz, so approximately 32 microseconds. And we will use, what we'll use is a duty cycle of 50%, okay, duty ratio of 50%. So I'm defining initial voltage when it's on. The delay, I don't have to take care about it. The on time and the total period time. Okay, the total period. So because here we consider 50% duty ratio, the on time is half the total period. So now I have the transfer part from the piezoelectric element or from the left part to the inductance. I just have to put the last energy transfer to the actual load. For this, I just put the diode as previously. I use the same diode. So again, it's not that, sometimes it's not good to use the generic models. So I'm just adding my diode. And the final capacitance. So this one, we can make it maybe bigger. 100 microfarads, okay. And the final connection, okay, and see what happened here. Actually, should have put some name, so positive output, negative output. Okay, I run it again. You see, when I plot, I can also make some operations. So for example, I can do positive output minus negative output, just to have the true voltage here. So maybe I took something a little bit too big. Actually, what you can see here also is that thanks to this decoupling, I can have voltage higher than the piezo voltage itself. So in red, it's the voltage at the end of the converter, and it can be higher than the piezoelectric voltage itself. In this case, it's normal, it's higher, because we don't have any load, so that means we harvest energy, we're accumulating the energy we are harvesting. Capacitance, transferring it here, that is then transferred back to the final inductance, final capacitor, sorry. And you can can be battery, for example. Here I just put a capacitance to make it simple. You need a smoothing element. You need a smoothing element. It can be, you can connect a resistor at the end, but you still need a smoothing element like a capacitor. And after, exactly, like it's made here, there is actually a load at the end. Actually, I'm afraid that here we won't have the time.
What is giving me?
What are you looking at?
I don't know, I just say run and I click here.
Yeah, but you are looking at the current. Look, it's the current over your... And actually, you can also looking at the current. You see, for example, here I have tens of volts and so on. But we can also, for example, have a look to the current in the inductance. Actually, it's no longer discontinuous mode. I will try to see where there is discontinuous mode, because this is this mode that is interesting. Whoa. Okay, maybe I will add a resistance to ensure that I'm operating in discontinuous mode. So up. I should have something more. I should find something more with more capacitance to limit the effect of the discharge. Wow. And actually, we can have a look to the current with considering the switching in order to validate what we saw previously, to check that we saw previously. We had actually here in this example, we can see that it's no longer operating in discontinuous mode. Okay, there is a non-zero mean current, and actually the current doesn't cancel. So for example, here it's not operating in discontinuous mode in this case. So that means we should maybe investigate a little bit more the operation and so on. Okay. Fortunately, we don't have the time for this right now. And let's go back to presentation itself. So actually, we can do, for example, here what I did is I changed the load in parametric analysis. Here I give some hint for the parametric analysis. Okay. And we used, actually in our case, we used external voltage, okay, for controlling the transistor. In practice, what we can use is a very low power clock. This is a clock that consumes, this example is a clock that consumes 0.3 microamps. So that means it can be directly powered by the rectifying capacitance, and it gives the control of the transistor, so that at the end we have a truly self-powered system.
If we have a very low voltage, we can change the diode.
You have
Some other type of non-silicon.
with Schottky diode, the problem, for example, with Schottky diode is the leakage current. You have reverse leakage with Schottky diode, for example. So it's kind of a compromise between the threshold voltage for forward threshold voltage and leakage current, inverse leakage current. Yeah. Most of the time it's too leaky. Yeah, there is. You can also consider some active diodes in particular cases. It's more interesting than it's also quite leaky, but it always depends on the electrical parameters of the piezoelectric element and so on. Usually, there is a trade-off to work on. Okay.
There's not another way of rectifying. So I was checking internet so much that these kind of rectifications add a lot of consumption to a circuit like this, or piezoelectric system.
Yeah.
Just kind of pseudo version.
No, actually, there are many ways of rectifying. You have also active rectifier, active diodes. You can have also mechanical rectifiers, things like this, but there are still some research to make about them. Sometimes active diodes are working quite well, however. You need to bring energy to op-amps actually. Okay, another way for ensuring that we are adapting in terms of load is just to consider that. Is just to note that at optimized load, so that we are harvesting the maximum power, the voltage is half the voltage we would have without half the voltage we will have without the load, but still with the same damping. Okay, there is a big difference with the same displacement magnitude. So that means if we have a damping effect, it's half of the voltage we will have with the same damping. So in order to, from this observation, we can also consider some strategies that takes into account this advantage, this particularity of half voltage compared to open circuit voltage. How to sense the open circuit voltage? We can disconnect the harvesting element and the transducer, but in this case there will be a change in the magnitude for highly coupled system because of the damping effect, and the sensing will be a little bit wrong. The second possibility is to add another sensing element like a piezoelectric system, and in this case we can compare the time when we have half of the voltage. Okay, I won't detail it too much according to the remaining time and overdue time already as well, but I got a grant to continue. There is also another thing is with TEG, you have very low voltages. In the example we had, in terms of heat body energy harvesting, we saw that we had something like millivolts. Okay, how to be able to harvest from this? Actually, here the principle is to use oscillators. So usually we used either oscillators with transformer that can be quite big, or integrated oscillators that can be quite costly. Okay, compared to off the shelf. One possibility is actually to use very classical way of having an oscillator, but introducing a bias. Like this, what we have, you see here it's the input voltage from the TEG. And what happened is that this is a normally on transistor. So when we have 0 here, it's conducting. Okay, no, sorry, when we have 0 between the gate and the source, it's conducting. So we have current going from the source to this other part. In this case, after a while, the gate voltage will decrease, and then we'll have the transistor that is blocked. And like this, we'll have kind of current pump between the two inductance. And thanks to this current pump and through the inductance ratio, we can have something actually that significantly magnify the voltage, especially because here with this bias capacitance, we are not clamping our voltage due to the inverse conduction of the transistor. Okay, this is experimental. Experimental measurements with TEG, so thermoelectric module voltage of something like 50 millivolts, we can have 1 volt and up to 6 volt with less than half a volt. And here it's actually it's oscillation, so that means with 0.4 volts we have 12 volts of oscillation. So it's something that can be used. Actually, we also use it to power microcontroller directly with a thermoelectric module. Maybe this time we won't go through the simulation, but it's quite quick to do if you want to do it at home. So here kind of TEG, and then here I have my system, and actually we can see that with 40 millivolts here we can have several volts at the output. So it helps also in converting very low voltage into voltage that are compatible with typical electronic systems. Finally, it's also important to have some regulation, voltage regulation, because if you apply 15 volts to a microcontroller, I'm not sure he really appreciates it. Or you can make a single-use fume generator. And therefore, it can be interesting to have a kind of voltage regulator that ensures that the output voltage has a given value. And to be honest, in this case, there is nice research, nice commercial systems that are available. Again, I'm not employed by Linear. I don't have any money by Linear. Actually, if they want to do some, I won't. But they have kind of dedicated product line to energy harvesting that can be also useful in the design of a system. Okay. So this leads us to the last part of this presentation and labs on energy extraction optimization. So here it starts going back, and actually in this case we'll focus on piezoelectric system, but it can be applied to electromagnetic through the dual transformation, to pyroelectric and so on. Like, okay, as long as there is either inductive or capacitive behavior, this works. Okay, we need energy storage element. Doesn't work with purely dissipative element, but with energy storage that works. So we will focus in our case on piezoelectric system, but it can be applied to others. Let's go to the energy balance, with here this term being the provided force, the provided energy, sorry, this term being the kinetic dynamic energy. Here, so the potential elastic energy, lost energy, and what is very interesting is this term here, which is the converted energy. So if we convert more, we can change the material. That's more or less changing alpha. We can change the structure, which is also changing alpha, but we can also play on the electrical side. How? What we want to do is to, with a given alpha, so with a given structure, with a given material, to increase this term, so to increase the integral of the product of the voltage by the velocity. How to do so? There are two possibilities. Either I increase my voltage, and I decrease the shift, the time shift between the voltage and the velocity. There is a very simple way to do this, actually, is when the voltage is maximum, I connect it to an inductance. So the piezoelectric element is a capacitance. I connect it to an inductance, I have an oscillating circuit. Okay? And the inductance is quite small, so it's oscillating at a much higher frequency than the vibration itself. Okay? So I have this oscillation. But what happens if I open the switch after half an oscillation period? Like this, I have imperfect voltage inversion. Okay? Then, once I did this voltage inversion, I let my system doing its own life. And because we have a system that is dielectric, the voltage will be continuous. Okay? Until I reach a new, the next minimum or maximum or the next extremum value of the displacement, and I do the operation again. So what happened? First, compared to the open circuit voltage, I have magnified voltage. So voltage magnitude higher, much more energy that is converted. And the second part is that if I compare with the velocity, I have part of the voltage that is in phase with the velocity, so that when I do the product and the integral, I have also a great increase. So we have both magnification through the increase of the voltage, but also thanks to the shift of this voltage. You can see also that I have no external voltage source here. The only energy I would need is maybe to control the switch, but conceptually I don't have any external source here. Everything is, energy is consistent with, is staying within the system. Okay, so no external source, no external energy for on the power branch. This is something that is also adaptive. If I change my frequency, I just here the principle is to detect is to switch on minimum and maximum values. So it's a frequency change. I still detect correctly the minimum and maximum value. It's truly adaptive. And previously, as I said, instead of considering the voltage, I can consider the current and adapt it to electromagnetic systems. Okay. So this is the principle of what is called synchronized switch that can then be applied to energy harvesting. Okay. For example, here the switching element, I put it in parallel with the piezo, between the piezo and the harvesting, the rectifier bridge. And when the displacement is maximum, remember that this happened, this coincided with the end of the harvesting process. I do my voltage inversion. Okay, and like this, it's exactly what we did previously, except that in terms of initial condition, it's not minus VDC when we have minus UN. It's gamma, where gamma is the inversion factor times VDC. Okay, and like this, I do exactly the same steps. Compute U1, so that means the voltage, the displacement at the next harvesting event, and so on. I can therefore then compute the power. It's exactly the same step as previously in the standard case. Okay, and what we can see is that we can harvest much more energy. The value of gamma is typically, let's say, 0.8. Around 0.8, 2 over 0.2, I can harvest 10 times more energy than in the standard case. There is also a shift in the optimal loop. Okay. But you see here, just playing with the voltage, just with energy consideration, and here because it's the energy cycle, I can perfectly consider some energy cycle that is given by alpha U and V. The principle is actually to go from a cycle like this, okay, to a cycle that is with a much bigger area. Okay, so even in terms of energy, pure energy, don't need to just in terms of energy transfer system, I mean. Of course, there is some electrical consideration of electrical schematic, but the concept itself, it's not electronic and so on. It's just taking to account and taking to advantage the energy coupling aspect. Okay. So then I can also consider the damping effect. So in this case, it's also similar than previously. So we do the energy balance at the resonance. So that's why I don't have the kinetic and the elastic term. With here the harvested energy, but we have also to consider some lost energy within the switch, within the switching bridge. Okay, so it can be included within the expression of the displacement magnitude. And what is interesting is the curve that we'll see after, because there is another way to do is instead of putting the system in parallel, the switching system in parallel, is to put it in series with the harvesting stage. In this case, it's different than what we saw previously, because previously we put in parallel, but the principle were quite the same in terms of analytical, getting the analytical expression was quite the same than in the standard case. Here it's different. Because previously we were harvesting energy when the piezo voltage was reaching the voltage on the load. Here, actually, we are harvesting energy during the switch itself. Okay, so when we connect the piezo element, we are connecting the piezo element to the inductance, but instead of going back to the piezoelectric element, it goes on the storage capacitance, and this is how it works. So here it's more kind of a pulse charge, a pulse energy extraction. Okay, so it's a little bit different. And instead of having inversion around 0, we have inversion around the rectified voltage here. So this is what is changing a little bit, because this time we are inverting around non-zero value, which allow to have the voltage just before what is noted V big M, and after, in terms of absolute value, V small m, as a function of the displacement, okay, of the displacement magnitude and the rectified voltage. And then I can compute the power, because again, I can compute the energy by doing the integral of the product of the voltage, so constant voltage VDC, times the current, but in this case the current, it's no longer the variation of the displacement, it's just the variation of the voltage. Okay. Previously we had something that was lasting quite a long time, but without any voltage variation, so that the current was equal to alpha U dot. In this case, we have a change in the voltage, but this change is so short that we can consider that there is no displacement change, so that we can only consider the voltage aspect on the current. Okay, this is what is done here. So that I dt, it's actually C0 dV. Okay. Again, I can also make the energy balance, or in this case, the first harmonic approximation of the equivalent force to get actually the effect of resonance with the effect of damping. Without taking damping, we already also have a kind of gain, a little bit smaller than in the previous case. But what is, okay, I would like to show others. I will switch a little bit the way I present it, because we saw these two techniques. Maybe it's interesting to discuss a little bit about them. So here we have the standard case, so what we did previously. Okay, then I add the switching element in parallel. This is this curve here. Okay, so here I consider, I guess, inversion factor 0.7, something like this. So with respect to this one, we have more than 8 times more energy that can be harvested. Of course, it's also dependent on the load, but I can adapt my load with what we saw previously to work at this optimal point. For the other one, the series one, actually, we have still a gain, a little bit smaller, however, and the load is also shifted, is also a little bit decreased compared to the standard case. Okay, so now we can think, okay, I have inductance here, I have inductance here. In the previous case, for load adaptation, I also had a kind of inductance. What about combining the two principles? Okay, so what about actually using this inductance to store the energy before transferring? But in this case, the inductance won't be used in an almost independent way of the motion, but will be used synchronously with the motion. Okay. Previously, with the load adaptation system, so what we did in simulation, we were switching at very high frequency on the inductance, okay, and totally independent from the structure motion. So here, what about using a similar system, okay, but synchronizing it, like in this concept of a synchronous switch, with the vibration. This is actually the principle of what is called synchronous electric charge extraction, so SEC. where actually here, each time I reach a minimum or a maximum value, I discharge my piezoelectric element on the capacity, on the inductance. And when all the energy has been extracted from the piezoelectric element, I open the switch and then the inductance discharge in the capacitance. Of course, when we see like this, when we explain like this, we can say it's exactly the same. No, it's not the same, because here the system is very similar, but the switch, the control of the switch itself makes a lot of difference, actually. Okay, because here previously we didn't had the shifting of the piezoelectric voltage. Okay. And we didn't had also this open circuit conditions and so on. And actually what happened, okay, I give you the theoretical demonstration for free. But what happened here is that we have also this kind of voltage magnification and shift that we don't have when we drive at high frequency. And so we have a power gain. Okay, the power gain is not 8, it's a little bit small, it's smaller, but it's still a power gain of a factor 3 to 4 compared to the standard case. And also we have the decoupling between the piezoelectric element and the load, so that means theoretically we have something that is totally independent from the load, and also without any consideration about the operation, because the opening time is so long that we are insured, almost sure that we are, that at before the next switch, the inductance will be totally discharged. So it's also with, to some extent, less constraints compared to the load adaptation case. Okay. Now, as I told you also, the constant vibration magnitude is something that is that can be considered when we don't have big electromechanical coupling of the structure. When we have this big electromechanical coupling, we have to consider the effect, the damping effect, that can be reflected by K squared QM. Okay, so here we have the standard case, what we saw at the very beginning. We have the two synchronized switch techniques, the parallel and the series one, and we have what we just saw, the SEC. Okay. Note that for the standard parallel and series SSHI, here it's dependent on the load, and here it's at the optimized load that also depends on K squared QM. For the SEC, it's independent from the load. Okay, but what we can see first is that somehow the switching system allows to artificially increase the electromechanical coupling, artificially increase, because we shift the same power for a much lower value of K squared QM. So that's why I say artificial increase of the coupling by playing with the electrical quantity. So this is the first aspect. Second aspect is that, of course, because there is this shift, the plateau is also shifted, and after a while, honestly, there is no point in using such techniques. These techniques are very interesting, actually, only for low coupled, highly damped, or medium, or with medium damping and coupling systems. But actually, before going to structures with a value of K squared QM bigger than 1, it's very difficult. Don't remember among you who is working on very highly coupled, yeah. What's the value of K squared QM in your case? 6. And actually, it's your research area is to make something really, really, really coupled. And what in when you did the literature review, what was the typical coupling value you saw? Or maybe K squared QM. And K squared QM?
I don't remember.
I guess usually lower than 1, typically. After, of course, if you use single crystals and so on, there is no mean in using such techniques. Okay, in terms of power, I mean. And finally, the last thing also to note is that for the load decoupling technique, actually there is a decrease. So it's even worse for using with with systems with a high value of K-squared QM. You have a question? No, okay, just scratching your head. So how to make it? Actually, here we need to control, and it's almost the end. We need to control a switch. To control a switch, we need energy, which is quite paradoxal with the fact that we want to harvest energy. But the thing is that we can use part of the energy that is available on the piezoelectric system itself to actually power the switching device. And actually, in classical cases, okay, so in cases with few volts, with capacitance in the order of a few tenths of a nanofarad, we can do a system, actually this one, that use typically less than 5, or even maybe around 3% of the electrostatic energy on the piezoelectric element. So on one side, you multiply the energy by a factor of 8, and you need 3% of this energy. Globally speaking, you have still a huge gain. Okay, so even in a realistic implementation, it's something that is variable. Okay, so how does it work? Actually, here we want to make maximum detection. How can we make maximum detection? When we have a maximum or minimum value, that means that the derivative is null. Exactly. However, using the derivative is a little bit tricky with the noise. Something very close to the derivative, but mathematically a little bit different, it's the differentiation. Okay. Actually, derivative is the differentiation when you tend to 0 in terms of time step. But here, differentiation is nicer because it gives a kind of robustness with the noise and so on. So how to make this kind of shift for making the differentiation? We will use an envelope detector, but that is lossy. Okay, so we have our piezo voltage like this, and we, thanks to this envelope detector that will introduce a small delay as well, and some losses also. Green voltage around here. Okay, then so we have this the shift. Then we compare with a simple transistor, PNP transistor, the piezo voltage itself with its delayed version. Okay, when the delayed version is higher than the piezo voltage itself, that means that we pass a maximum value, and in this case, the transistor here will conduct and apply the voltage of this capacitor on the final switching transistor that will therefore conduct. So this is the principle on how the switch is turned on. But after we have to turn it off. Turn it off is actually at the end of the inversion when the voltage wants to go back if we let oscillating. But if the voltage goes back, that will mean that we have also the current that cancel and wants to change its signs. So we will prevent the current from changing its signs by using a diode. Actually, the diode here is used to stop the inversion. Okay? So this one is for maximum. If I want to do minimum, I copy my circuit and reverse it. So let's do it. Actually, we can also do externally powered, but we won't do this one. We can do like this. So the principle, so it's very similar again than previously. We have the same parameters. Hop. So we have the same parameters, and let's do our self-power switch. Okay, so the first step will be the envelope detector. So we need to choose resistance and capacitance value in order to have a time constant that is compatible with the frequency. Okay, so in this case, what is, and also, sorry, a capacitance that is not too big with this one. Otherwise, we will modify the behavior of the electrical behavior of our source. So it should be quite small. So we have 50 nanofarads here. So here 1 nanofarads. It's small enough to be negligible. Okay. In terms of resistance, we can, for example, put 56K in order to have a time constant R times C that is compatible and to ensure that it will be discharged at the end of the next conduction period, so half a vibration period. As previously, we won't use the generic diode model. Okay, we will use a dedicated, an existing model actually. So I'll connect them. Okay. I can, while constructing the circuit, I can make some intermediate check. For example, I can run and looking at as a function of the value, the piezo voltage. Okay, I don't need too much. I don't need too much periods. So the piezo voltage with the envelope. So right now, you see, the envelope is not discharging. That's normal because we didn't control. We are not controlling the transistor yet. Okay, because the idea is also to discharge the capacitance through the transistor. Okay. So it's just here. You can see we have the envelope. We have the envelope. Then we will also make the comparison. So in this case, we are using a bipolar transistor, and more precisely, PNP bipolar transistor. I also add a big resistance on the base to limit the current that is actually taken from the piezoelectric element. Okay, so 4.7 megs, for example. And in this case, it will be sensed also. I connect it to the piezoelectric element. And the other side, on the emitter, I connect it to the envelope detector. That's making my comparator. So now I have my transistor that can be used as comparator. I can check that everything is going fine. So here I will add also to ensure the discharge of the capacitance, I add a resistance. So now we'll add the final switching element, that is the MOSFET. Okay. So let's add it. As previously, we'll take also the same. So again, we do pick new MOSFET. I sort it alphabetically, alpha numerically actually, so that the one that actually is interesting is the first one, 2N7002. Okay. And right now I'm not connecting it because I want to check that everything is going well. Okay. And if I'm looking at here, you can see, so in red, that's the command of my transistor. And you can see here that when I have maximum value, I have a voltage that is applied on the transistor. So I have 0 voltage applied on the transistor, and this is what will initiate the inversion process. So actually here, I guess I can go, I can continue. So here, I will also add the inductance, okay, the inductance to stop the inversion. And if I do like this, actually, I just do something on the positive value. So it cannot work. There is half missing, and half is for the minimum value. As we said, to go from the positive value to the negative one is just copy and just inverting the terminals. Oh, sorry. Actually, I have the problem here is that because I have the same name. So when you put, actually, that's also nice to make the mistake, because I can also share with you some basic error. Actually, when I do the copy, it happens actually so often. When I do the copy, it also make the copy of the label. And if there is two labels with the same name for the software, that means they are connected. So in this case, he thought these two wires, these two nodes are connected. So that's why there was some problem. And like this, you can see here the piezo voltage that is indeed inverted. Okay, maybe I will add some losses in the inductance, because otherwise it's not that realistic. Up. And so we see this inversion when the piezo voltage starts dropping. We'll have the application of the voltage on the transistor that will therefore initiate the inversion process, and so the voltage inversion will start, and we'll have actually the voltage inversion. You can see here there is a transient stage for charging the capacitance. And if I compare here the case with and without the switch, so here we'll call it PZT2. If I compare with or without the switch, you can see that we are going from approximately 40 volts to here. Of course, it's simulation. Be careful with this. To something almost 300 volts. It might be possible under some circumstances, but be careful with it. It's still simulation. But you can see that here, I don't have any external power source except than the piezo. Okay? And actually, the piezo, it's also itself used for energy harvesting, but totally self-powered and also self-sensing. I'm using the same piezo to detect the maximum and minimum values than the piezo that is used for the inversion. So it's self-powered and self-sensing as well. And at the end, I can add the harvesting stage either with a full rectifier bridge or with a voltage doubler in order to limit the losses within the diodes. Okay. I won't go too much into detail, but there are a lot of derivatives based on this. I gave you the original ones, so the one with voltage inversion and the one with voltage cancellation. But there is also a lot of derivatives, either with several steps, combining, for example, SEC and SSHI, with slight modification, for example, SEC, what was done by Elie Lefebvre, doing the SEC without totally cancelling the voltage, using other kind of magnetic elements, using a transformer to limit the voltage drop on the diodes. Also some kind of a little bit more smarter way of doing, especially in the case of a multimodal system. So avoid over-switching to let energy entering to address actually the issue of the damping. Also, as I told you, to extend it to electromagnetic systems, and so on. This And thank you, Professor Mitchelson, for having given me the time for finishing this lecture. So in terms of summary, first we saw that the choice of the energy source and the associated conversion for energy harvesting strongly depends on the application. Okay, but in a general way, thermal, vibrational, and solar energy are usually the most considered. That designing an energy harvester, it's not only doing a material, not only doing mechanical or heat transfer, then doing electrical, and then doing a microcontroller. It's a whole, okay? And because it's a whole, you have to make a kind of global design. And also because it's a whole, you have to make a clever use of the energy. Okay, so really thinking really as a whole, because the energy chain is not unidirectional, and because there is no point in trying to increase by 50% the harvested energy if the sensing function is not well done. Okay, things like this. Actual challenge actually is to ensure that we let more energy entering in the system. Okay. Also, in the case of vibrational system, is to be adapted to large bandwidth, for a large frequency spectrum. Okay. Also, to ensure that maximum energy is extracted, whatever I have connected to my system. And also to convert the maximum part of the incoming energy. Okay, so basically we saw in terms of electrical interface that we can decompose, roughly speaking, into three stages. The first one to ensure that the load, energy harvested is optimized, whatever the load. Especially we saw the use of switch converter in discontinuous mode operation, discontinuous conduction mode operation. We saw also the principle of the switching devices. Hola. If I break it, I think I will be homeless after. The use of switching interfaces in order to artificially increase the coupling coefficient, okay, and to harvest more energy, especially when we have a system that is with low coupling coefficient or with high damping. Otherwise, there is no point in using it, well, honestly. And finally, there is also the voltage regulation, but for this, to my opinion, I think there is enough advance in terms of commercial ICs for voltage regulation. Okay. We saw how to implement on simulation, even if sometimes it was quite fast. Sorry about this. We saw that that we can also represent our transducer as an electrical equivalent circuit. That can be quite handy for simulation. But again, and I insist on this, it's a tool. It's not. It's something that we should be aware about. All the tricks and all the dangers about it. Okay, and we saw how to represent our transducer, even if there is a loss in terms of physical meaning, because here that's a mechanical aspect in the electrical domain. So it's a little bit strange. How to implement some switching elements, especially we designed ourselves the self-power switch. And again, yeah, simulation is useful, but that's still a tool that won't replace any analytical expression, so theoretical development, and also some experimental validation. Sorry for this quite long talk. Hope you appreciated it anyway. And thank you very much for your patience.